Section 9.4 is called Permutations and Combinations. And we're going to use these as they relate to probability, and you'll see how as we get going. But the first thing we need to do is a little bit of notation that you may or may not be familiar with. That notation is an exclamation point, okay? An exclamation point in mathematics has not an, hey, look, I'm excited kind of meaning, all right? What it actually means is it means multiplication of the number that you're starting with down every number till you get to 1. So for instance, if you're doing n, and this were your number, you'd take the number n times the number n minus 1 times the number n minus 2. You just keep going down the line, all the whole numbers, until you get down to 1. Just multiply them all out. And by definition, we need to know what a 0 factorial should mean, and it is defined to mean the number 1. So if you see 0 factorial, it means 1. Okay? Okay, so we'll do an example right off the bat, real quick. 4 factorial. What should that mean? You got it. 4 times 3 times 2 times 1. And what would that be? 24. All right, so now you guys are experts in factorials because that's exactly how simple it is. Just multiply all the numbers lower than it. All right, another principle that we encounter, and this actually comes from number theory, but I know not all of you have taken it. It's called the fundamental principle of counting. It says, if event M can occur in m little m ways, and event capital N can occur in little n ways, in how many ways can event M followed by event N occur? And the answer is you multiply the number of ways they individually occurred, little m times little n. And in some sense, we've already done this every time we've worked with our tree diagrams, right? Every multiplication along every branch of our tree diagrams used this property. How do you get a 1 and then a 2? Well, how many ways do you get a 1? How many ways do you get a 2? And we go from there. So if we're doing an example, Pizza Planet, which is from Toy Story, fantastic. Actually, I've been somewhere and they had a Pizza Planet. I didn't eat there, but I did see it from the car, and I thought that was interesting. Pizza Planet offers 3 kinds of salad, 15 kinds of pizza, and 4 desserts. How many different meals consisting of 1 salad, 1 pizza, and 1 dessert can you create? Well, these are the capital M's and N's that we were talking about on the previous slide. So in how many ways can you have a salad? 3. And a pizza? 15. And a dessert? 4. And we multiply those outcomes together. And what do we get? 180. So there are 180 meals. Okay, simple enough. Just multiplying outcomes together. All right. Now, the title of this section was Permutations and Combinations. There are 2 types of permutations. You need to know the difference between them. The first type of permutations is of like objects. If you have n elements and you choose R1 of which are alike, R2 of which are alike, and so forth, then the permutation is found by taking, the number of ways that this can happen is found by taking n factorial over R1 factorial, R2 factorial, Rn factorial, all the way down. Okay, like objects.
What would an example of that we're about to do?
We are about to do an example, yeah. As a matter of fact, I almost kind of wish I could change the example because I've been stuffing Easter eggs with jelly beans. Jelly beans are a fantastic example of this, but the Starburst in my next example will work too. A package of Starburst, it's a little bit smaller numbers, which is why it's actually being used, because the jelly beans have lots of jelly beans in a bag. Starburst don't have lots of Starburst in a container, right? In a package of Starburst, there are 4 red, 5 pink, 3 yellow, and 2 orange. That would be a very good container of Starburst because it has the most pink, just so you know. Got to have more pink. And my Starburst jelly beans, the pink ones are the best too, just so you know. Starburst jelly beans, they're awesome. In how many different ways can you eat the Starburst? Well, see, here's the deal. If I eat the pink that came at the top of the package or the pink that came in the middle of the package, that's a non-discernible, difference of way I could eat the pinks, right? Because the pinks taste the same, whether they're at the top of the package or the middle of the package. They're like objects. But if I ate a pink and then a red, that would be different. It would be distinguishable than eating a red and then a pink. Are you guys with me? Okay, so there are duplicated items within this category. Lots of pinks, lots of reds, some oranges, and some yellows. So that's what makes this a permutation of like objects. Some of the objects are flat out alike and there's no way to tell them apart. Yes? That's why we're using this. So, how many Starbursts do I have? There are 14. So my numerator is 14 factorial. My denominator is each one of the different things that we have with a factorial. So, how many, what did I start with? Red are there? 4. So I have a 4 factorial down here. How many pink were there? 5 factorial. How many, what's next? Yellow were there? 3. You can have all my yellow Starbursts, just so you know. And orange? 2. This will find the number of different ways that you could eat that package of Starbursts. Okay, you ready to take a look? All right, well, I don't really want to multiply 14 times 13 times 12 times 11, and I really won't want to do it in a minute here when the number's bigger than 14. That is not an effective use of any of our time. But what we are going to do is we're going to write out what it is until we get to the largest value that's duplicated in the denominator. So what's the largest value right now in my denominator? 5. So we're going to write this out until we get down to 5. And it is 5 factorial. I don't just stop at 5. I still have 5 times 4 times 3 times 2 times 1 at the end. I just am sort of truncating how I'm writing them. I'm writing them out as 5 factorial. And the reason I'm doing that is because I exactly have a 5 factorial in my denominator. In fact, I'll write it first just to make that emphasized. There's a 5 factorial down there already, which means the numerator has 5, 4, 3, 2, 1. The denominator has 5, 4, 3, 2, 1. I'm just not going to write them all out. I'm going to cancel them because they're all exactly the same. You can only do it if they're exactly the same. So I can't like reduce the 5 factorial with a 10 on top, right? Because 5 factorial means 5, 4, 3, 2, 1. So I can reduce these two because they're exactly the same, 5, 4, 3, 2, 1. Now it's not all I had in my denominator. I also had 4 factorial. So now I'm going to have to write that out because I do not have a 4 factorial now in my numerator. I had a 3 factorial, so that's 3 times 2 times 1. And I had a 2 factorial, which is 2 times 1. Now here's the cool thing about everything we're working with today. Every time you find a permutation, or in a minute a combination, everything in the denominator will reduce with something in the numerator. It will. Now, could you actually take your calculator and multiply everything on the top together? Sure. You can't when the numbers get too big because it'll turn it into scientific notation. But on this one, sure, you could. But it's also possible that you could combine a few things on bottom to cancel. For example, if I take the 4 and the 2 and the 8, wouldn't those cancel? Sure would. And now I've got less to work with than I did before. What else do you see that you could reduce? Maybe not quite like that, but you could reduce it somehow.
3 and 3 and 9.
All right, 3 and 3 and 9. That one would work. What else? Some of you said 3 and 6. You could have done that instead. It'd be fine too instead. How about 2 and 6? I can reduce them. I just still have a 3 on top. Exactly. There's still a 3 up here, so don't forget about him.
And then the 12 or the 14, 2.
Whichever one you want. We'll do 14 since you mentioned it. So the 14 and the 2 in the denominator gives me a 7. Now here's the catch. You've got to be really careful not to lose any of these guys on top because it's easy to do. So right now you have 7, 13, 12, 11, 10, 7, and 3. Don't forget the 7 that's over there. Right? So you grab your calculator and you're going to multiply 7 times 13 times 12 times 11 times 10 times 7 times 3. And what do you get?
2,522,500.
There are 2.5 million ways of eating a package of Starburst. Who knew? Crazy, right? Yeah, crazy. All right. Now, what happens then if the objects are unalike? They're different. All the objects are different. So, you had the Starburst package, but every single one of them was different, right? Well, that would be different, right? I wouldn't have anything in the denominator to worry about. Agreed? None of those values in the denominator would have happened because none of them would have been duplicated, okay? Well, a permutation of unlike objects has the property that order matters. It mattered on the other permutation too, okay? That was the whole point. We were trying to find the number of orderings that we could get for these things to happen. But this is when order matters, all right? So I'm going to give you an example where order matters. If you are running a race where there's a first place, a second place, and a third place prize, medals, ribbons, I don't care what they are, does the order matter? Of course, right? You get the gold medal, you get the bronze medal. That's different. You're in the Olympics. They play your national anthem or they don't, right? It's different. Order matters. Okay? But there are races that can be run where the order that you finish isn't exactly mattering. So I know I've got a couple of you in here at least who do run, maybe some of you who swim or other things as well. But have you ever been in a qualifying round of something? In a qualifying round of races, it doesn't matter if you're first or say maybe second or third. All that matters is that you're in the top so many. The top 3, the top 4 move on. You guys with me? So it doesn't really matter of the order, it just matters that you made the cut. So in that case, the order wouldn't matter. In that case, you have something called a combination. Okay, so permutations, order matters. So let's do an example. Oh, I need to tell you this, sorry. The way you calculate a permutation is that you have n items and you're choosing r of them. So like you have 15 runners and you're choosing 3 of them to get the top 3 prizes. Okay, so you have 15 factorial and then r would be 15 minus r, and 15 minus 3 would be 12 factorial on bottom. That's how that works. So let's do an example where it's not that example, but a different one. 30 contestants put their name in a hat for a raffle. First place wins $100, second place 50, and third place 25. Does it matter the order in which you win? Sure does. You get different amounts of money. In how many different ways can the prizes be awarded? Well, it says 30 contestants, so there's 30 people that we're picking from. How many people win prizes? 3. So this is 30 choose 3. My formula is 30 factorial on top. And then in the denominator, I have 30 minus 3. Basically, I have the number of losers in the denominator, don't I? I do. So in my numerator, I have 30 factorial. In my denominator now, I have 27 factorial. Everybody good so far?
Where did we get the 30 and the 3?
Because there are 30 people who put their name in the hat.
Okay.
And there are 3 people who win. Yes. Okay, any other questions so far? Okay, 30 factorial is too big for your calculator. Some of you have calculators that have a factorial button in it. Leah, hold yours up. Hold yours up. TI 83, 84, those kinds of ones, those have them in it. Isn't that what yours is? Is yours a TI?
No.
What is it?
FX9.
Is it Casio?
Mine's a TI, but I
Okay,
don't
that one
see
still
it.
will do it. It's in there. Those of you who have those kind of calculators, in fact, most scientific ones probably do too. I'll show you where it is. But if you try to multiply this out, even by hand, it's going to be too big, and your calculator is going to turn it into scientific notation. Okay? It's not going to be helpful. You wanted an exact answer. So what do we need to do? Well, this one's really nice because you can just write it out until you get to 27. And then you've got the 27 factorial in the denominator. That cancels. So what do you really have to multiply? 30, 29, and 28. That's it. That's all you have to multiply. 24,360 ways. Make sense? Okay, but like I said, the order doesn't always matter. If it doesn't matter, it's called a combination. Take a look at this formula. What's different about this formula than the last one?
You have n minus r, but you can multiply by r.
Yeah. This piece is the only difference, right? We've got an r factorial in the denominator. It's the only difference. Now, if the order matters, should there be more ways or fewer ways for something to happen? If the order matters. If it matters the order, there's more ways, right? Because if the order doesn't matter, like if the order matters and I've got three winners of a race, then I could have Julie in first place, second place, or third place. But if Julie's in first place, then I have Heather in second place or third place, right? But if all I care about is that Julie, Heather, and Jill are in first, second, and third place, then it doesn't matter whether they're first or second or third, and I can move them all around, and that's all the same thing. But if the order matters, there's more options of how that could happen. So if you take a look at this equation, and I've got an extra r factorial in the denominator, I'm going to get fewer values for combinations, right? Because I'm dividing by more stuff. The number is going to be less. So this is my example, very similar to the one before. 30 contestants, put their name in the hat, top 3 people, all win the same thing. So does it matter if you're drawn first or second or third? Not at all. Makes no difference. You get the same prize. So what would this look like? Well, a combination. So this is 30, C3. C for combination. 30 factorial on top. And I have the same 30 minus 3 on bottom. Same as before, but what else is on bottom? 3 factorial. Okay, so I still have 30 times 29 times 28 times 27 factorial. All of that's the same. And I have a 27 factorial on bottom because that's the 30 minus the 3. But I also have 3, 2, and 1. So the 27 factorials cancel. Again, if you want, you multiply the numerator out, divide by 6. That's fine. If you want, you could reduce the 3 and the 2 right here as well. The 3 times 2 is 6, and 6 reduces in 30, doesn't it? What will the 30 become? 5. So you could simply write this then, or think about it as 5 times 29 times 28. What are you going to get? 4,060 ways.
How is this formula different? I missed the slide.
Compare the equations, Hannah.
Okay, that's what I thought.
Yep, compare the equations. This formula has an r factorial in the denominator, so it's going to give us a smaller value. And it did, quite a bit smaller, right? This one was 24,000, and this one is, where'd it go? 4,000. It's considerably less. And depending on how many things you select will depend on how much less it is. All right, so we're going to do a few more examples now. Some of these are, there's 4 different kinds of problems here, okay? This is important for you to realize. There's problems that are like the Pizza Planet problem, okay? Where it's just multiplication of different things that can happen. There are problems that are permutations of like objects, like my Starburst problem. There are problems that are permutations of unlike objects. That's where the 3 contestants win, but they win different amounts. And there are problems that are combinations, which are the 3 contestants winning, and they win the same thing, so the order doesn't matter. So as you're looking at the problem, you have to figure out what type of problem it is. And sometimes you actually have a choice, and you can do it one way or another way and get the same answer. So there's one example I've got in here like that, and I'll show you when we get to it. Here's our first one, example 6. If all phone numbers in a large business are 405, 767, and then 4 more numbers, how many different phone numbers are possible?
So that would be combination, right?
Combination, the order doesn't matter. That's a true statement. But in a combination, you can't repeat things.
So it
Now, but again, does the order matter in a phone number?
Yes.
Madison.
Well, like, yeah, but like finding it. I'm trying to.
If somebody types in the phone number 405-767-1234 or 4321, do they
Oh,
call a
yeah.
different person? Yes.
Okay.
So this wouldn't be a combination under any circumstance, actually, because the order actually would matter, right?
Okay.
But it's actually worse than that. I mean, not only does the order matter, you can repeat things. Right? If I'm eating my Starburst, I can't well, I'm hoping that I can't repeat eating the same pink Starburst. Right? That'd be gross. I mean, like, come on, right? Okay, so you have to think about whether you can repeat things. You can repeat things here, yeah? Okay. So this is not a combination. It's not a permutation. What is this? This one is a fundamental principle of counting. It's like the Pizza Planet problem. I have 4 choices here. How many different choices do I have in the first number slot? 10. How many choices do I have in the second number slot? 10. And the third one? 10. And 10. Just like my pizza salad, I was about to say breadsticks. I think it was dessert, though. See, pizza salad and dessert. What do you get when you multiply these together?
No,
1,000 or 10,000?
10,000.
I think 10,000 is what I have written down. Okay, good. So there are 10,000 different phone numbers. If they need more than that, they've got an awfully large business, agreed? 10,000 would be a lot. All right. This is an example where there are 2 ways to do the problem. A worship team practices 8 songs on Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? So somebody give me a thought on what you might do for this problem.
Would the order not matter because you could have songs, you could have the same song but in a different order? It would be kind of like the problem with the raffle where everybody gets the same prize. It's just a matter of
Okay, so let's start with that part of what you're asking then, Catherine. Okay, so you're looking at this, is it a permutation or combination question, right? Does the order matter? So this is one of those. It is a problem where it's either a permutation or combination. That's one way to do it. So the question I'm going to ask you is, does the order of the songs matter?
It says how many ways can the songs, and how many ways can the songs occur, so does that mean the order does matter?
It does by the very nature of how it's worded. That's a true statement. But there's something else going on here that you guys should feel like you should be aware of.
Well, if they're like, it depends which one he picks by what they're listed at.
Okay, so have you guys been in a prayer service, or a church service rather, where it's prayer time? Yeah, prayer time in the church service. Has your pastor ever played My God is So Big at prayer time? My God is so big, so strong. Bible, prayer time. Probably not. Probably played something like 'Tis so sweet to trust in Jesus, or I love you, Lord. Okay? Does it matter the order of the songs? Yes, it does. It really matters, right? That's what the worship minister is trying to do, is they're trying to create a sequence of songs that make sense in terms of the order of the service, right? So the order does matter. So since the order matters, is that a combination or a permutation? It's a permutation. So one way to do this is a permutation. And the permutation would be to have 8 songs, because that's how many we have, and choose 5 of them. So in terms of mathematically writing this out, this would be 8 factorial over 8 minus 5 factorial. What's 8 minus 5? 3. So I have 8 factorial over 3 factorial. So what am I going to do to find this?
You're going to make it 8 and 4 times 7.
And I'm going to stop at 3 factorial because that's where it matches, right? Identically matches the other one. And the 3 factorials cancel. All right, so what is 8 times 7 times 6 times 5 times 4? 6,720. Okay, so one way of doing this problem is as a permutation. There is another way of doing this problem. Did anybody think of something different? What'd you think of, Abby?
We do like the same thing we did in the last problem, but we have like 5 slots, I guess, and then do 8, 7, 6.
Yeah, this one actually works out to be thought as a problem where it's a fundamental principle of counting. Yeah, I've got 5 slots in which to put my 8 songs. I can do this because the order does in fact matter. So the first slot, there's how many choices? 8. And then once I've done the song, we're not going to do it again. Okay, 7. Down the line. And of course we have the same digits that we just had a minute ago. That's not by accident. But we still get the 6,720. Either way is completely and totally correct. This should say ways.
Can you only use the fundamental one if order matters?
That's actually a true statement, yes. If the order did not matter, you would not have been able to use the fundamental theorem of principle of counting. That's correct. All right.
How does it matter with the very first problem we give pizza?
How does the order matter?
Yeah.
It didn't. It was a number of ways of different things happening where we weren't repeating.
But I thought you said with the fundamental counting, the order does have to matter.
Yeah, because we were selecting from things where we were repeating options.
So you can use the fundamental order even if the order doesn't matter.
Yeah, because when we did our pizza planet example, those 3 options were 3 completely separate things totally. Like let's say, for instance, though, that you were doing the pizza planet example and you needed to order 2 pizzas. Well, that'd be tricky because 2 pizzas, does the order matter or not? Well, probably not, and then we'd run into some problems because we had 2 pizzas we were ordering. The reason it worked with our pizza planet example is because we were just picking one item.
Okay.
On the ones that we're doing on this one and on the last one, we were picking multiple from among the same things, multiple songs from among the same songs, multiple numbers from among the same numbers. All right, my last example that I'm going to do is all about a deck of cards because it lends itself well to asking several questions about the same stuff, okay? So we're going to start out with a 5-card hand of cards. Have we talked about cards in this class?
Yeah.
Yes, excellent. I think we did it with 9.1 actually. All right, so we have 52 cards and we're going to select 5 of them. So here's my first question to you. Does the order matter? No. In fact, every card game that you've ever played, the first thing you do when somebody gives you cards is you do what with them? You shuffle them in some kind of order that makes sense for your hand, right? Depends on the game. Do you organize them by color, by suit, by number, it depends, right? Every card game. We've played Phase 10 at my house recently, and I look sometimes at my children's hands, and I don't know how they can see anything in their hand because they didn't organize it how I would have. You guys know what I'm talking about, right? They just didn't do it the same way you did it, okay? So the fact that you can move them all around means that the order didn't matter in how it was handed to you to begin with. So if the order doesn't matter, is this a combination or a permutation? It's a combination. It's 52 items, and we're choosing 5. So far, so good? What does my numerator look like then? 52 factorial, which is definitely too large for your calculator to deal with. What's my denominator look like? Fabulous. 52 minus 5 factorial and 5 factorial. So I have a 52 factorial on top. On bottom, what's 52 minus 5? 47 factorial, and I have 5 factorial. Notice the 47 and the 5 add to the 52, right? All right, so I'm going to write the 52 out till I get to what? 47 or 5? 47. Save yourself some time. 52, 51, 50, 49, 48, 47 factorial. There's my 47 factorial on bottom. And then I have 5, 4, 3, 2, and 1. All right, 47 factorials cancel. Again, if you want to multiply across the top, multiply across the bottom, that's fine. I like to reduce things. So, for instance, I noticed that I've got 5 and 2. 5 times 2 is 10. Well, I can reduce a 10 with a 50. That gives me a 5 right here. Sorry, that yellow is absolutely awful. I can't do that to you. Let's do orange. How about a 5 there? 4 times 3 is what? 12. And 12 will nicely reduce with 48 to give me a 4. Again, you don't have to reduce them in that way. You can reduce them one at a time, but that's just the ones I saw this time. So the result that you have, be careful, is all the numbers that are left. 52, 51, 5, 49, and 4. What does that give you? There are 2,598,960 hands of cards. 5 card hands of cards. That's a lot, isn't it? Wow. All right. But what if we wanted a hand of cards, or we want to know how many hands of cards are all diamonds? There's not as many diamonds, right? How many diamonds are there? 13. Is this a combination or a permutation? It's a combination. The order still doesn't matter, right? I just want them to all be diamonds. So I have 13 to choose from, and how many am I choosing? 5. So this is 13 C5. This will be a much smaller number, obviously, because I didn't use a 52, I used a 13. 13 on top. What goes on bottom? All right, does that look good to everyone? So I have 13 factorial on top. 13 minus 5 would be 8. So I have 8 factorial and 5 factorial on bottom. So I'm going to write out my 13 until I get to what? Please make note, I'm writing 8 factorial. Don't just write down 8 and stop. You have to have 8 factorial to match with the 8 factorial on bottom. And then 5, 4, 3, 2, and 1. Excellent. So there's my 8 factorial. It's gone away. Group something together for me. 5 and 2 make 10. Fantastic. 4 and 3 make 12, leaving me with 13, 11, and 9. What is 13 times 11 times 9? 1,287. All right. Now, part C is a little different. Part A asks for the number of ways of getting all hands of cards. Part B, the number of ways of getting all hand diamonds, right? All diamond hands of cards. All hands of cards that are diamonds. I can't even talk right. What is part C asking for? It's asking for probability. Not the number of ways things can happen, but the probability that something will happen. Okay, so put your probability hat back on. We want the probability of getting 5 or all diamonds. How would I do that?
It's match the previous answer over the, like, it's what we got for B over what we got for A.
Yeah, so I'll write it properly. It's the number of ways of getting all diamonds, which we found in part B, divided by the number of ways of getting any hand of cards. And we found that in part A. So this should be 1287, that's what you got from part B, divided by 2,598,960 from part A. And we'll write this down as a decimal, and we'll go with 4 decimal places, because 3 is not enough. What do you get? 5, yeah. There, and if you turn that into a percent, just to kind of give you some perspective, that is less than a 0.05% percent chance of that happening? It's not very likely, right? Not very likely. All right, so in an effort to say that we don't always use this for card games, which is a true statement, let me show you how you can use it for something that's not a card game, but in the same way. We've got a committee of 3 people that are selected at random from 7 seniors, 5 juniors, 3 sophomores. Okay, going to make a committee, 3 people. What is the probability that the committee consists of all seniors? Well, let's just write it out like we did on the last one at the beginning, right? The probability of 5 diamonds is the number of this over the number of this. Well, this should be the probability my screen's messing up, of all seniors. Okay, so this should be the number of ways of getting all seniors compared to what? The number of ways of getting anybody. Okay. Well, what's the number of ways of getting all seniors? What's the number of ways of getting anybody? See, in the last question, I sort of skipped. I mean, I didn't skip. I did parts A and B, and then we did part C, right? C was the probability question. We've sort of skipped parts A and B. That's what it's kind of like. I need to figure out the number of ways of getting all seniors and the number of ways of getting anybody. This is a committee. On a committee, does it matter if you're chosen first or last? No. So does the order matter? No. So we're going to be working with combinations. Okay, for which part, Leah?
For all seniors.
All seniors? Are there 15 seniors?
Well, that's those 15 together.
Okay. So it's the bottom. There are 15 people we're picking from, right? How many people are on my committee? 3. If I want the committee to consist of only seniors, how many seniors are there? 7. And I want to choose 3 of them. Is that okay? Makes sense now? Okay, good. So we're going to calculate each of the numerator and denominator separately now, and then we're going to go back into the problem and put those values in. Okay? So let's, how did I get what, Hannah?
3
Or
on the
Madison?
top. Like, you're only picking 3 even if it's all seniors.
There's only 3 people on the committee.
Oh.
So no matter who's on the committee, I've just got 3 people. Okay? Everybody understand where the 15 and the 7 came from? Okay, good deal. So we're going to calculate 7C3. So how does that work? What do I get? Okay, 7 minus 3 is obviously 4. So we're going to use 7, 6, 5, and 4 factorial over the 4 factorial we have. And then 3 factorial is 3, 2, 1. So my 4 factorials cancel. What else? 3 and 2 makes 6, so that cancels. So what's this total? 35. All right, now let's do 15. C3. So 15 factorial on top. Over 15 minus 3. That's a larger number. And then 3 factorial. So what's 15 minus 3? 12. So I'm going to go down to 12. 15, 14, 13, and 12 factorial. Over 12 factorial. And then I have 3, 2, and 1. What cancels?
15.
Okay, my 12 factorials cancel, and then 3 and 15, so that leaves me with a 5. 2 and 14 leaves me with a 7. So I have 5 times 7 times 13. What is that?
455.
455. All right, so there's all that work over there, written super tiny now. And up here, what is 7C3? 35. And what is 15C3? 455. You can either simplify that in fraction form. You can simplify to a decimal form. I think I have a decimal written down here. So for fun, what do you have? 4 places. We're doing 4 places for all of our probabilities here. What do you get? I think 769, yeah. So about a 7.5% chance, right? 7.5% chance that my committee is going to be all seniors. Let's do part B. What is the probability the committee has no seniors? Now, that is not the same thing as having not all seniors, right? Are you guys with me? Having no seniors and having not all seniors do not mean the same thing. So if this said not all seniors, what could I do?
Subtract it.
Yeah, I could just subtract it from 1. But this actually says no seniors, which means that I'm only able to have sophomores and juniors, right? So I want the probability of no seniors, which is the number of ways of getting no seniors. Again, or we could say all juniors, freshmen, sophomore, whatever else is there. And this is the number of ways of getting anybody, but we already found the number of ways of getting anybody, didn't we? What was it? Yeah, so don't do work you've already done again. This is 455. Can I find the number of ways of getting no seniors? Hang on, let me do it this way. Okay, so it's 8C3. That's what I heard Leah say. Does everybody know where she got an 8? Okay, so let's come down here and do my 8C3. What will 8C3 look like? Yep, I'm hearing a couple of answers that sound just the same. Fantastic. So 8 minus 3 is 5, so we're going to write out our 8 to 5, down to 5. 8, 7, 6, 5 factorial over my 5 factorial, and then I have 3 times 2 times 1. What cancels? 3 and 2 makes 6, and 5 factorial. So I have 8 times 7, which is 56. So over here I have 56 over, sorry, just a second, I'm not quite where you are. 56 over 455. And in decimal form, what was it, Leah? 1231. So it's slightly more likely, about 12% chance that I have a committee that has no seniors on it. So what's the probability that I have at least some seniors on there? If I had 1 minus this, I would have the probability of having at least 1 senior on here, right? So about an 88% chance of having at least a senior on there somewhere, right? All right, any questions on this? All right.